All right. I stayed up late last night and got the tests all graded and returned to you on Moodle. So here I'm giving you the paper copies, but you already have the ability to view it on Moodle. So I'm sure you probably already looked at it. There were two students that were in the ballpark of 104%. That was very good. That is, they pretty much got everything right plus extra credit. There were some who didn't get such good scores. There were some clear misunderstandings about crossing out the problem you don't want to be graded. I was a little lenient this time. I gave some people credit. They didn't cross any of them out, and they didn't attempt this one. They did attempt that one, so I just went ahead and crossed out one they didn't attempt, rather than sticking with the rule and crossing out the last one. I won't do that next time, okay? That was I don't want people to lose credit because they weren't quite clear on what they were supposed to do. But hopefully now you're clear, yes, you're supposed to cross the one out that you don't want graded, or else it's going to be the last one in the section.
Is there a particular reason you're going to do stuff like that?
It's just kind of a nervous habit.
Please stop.
I will stop for you, Russell. The solution, if you go to OneNote, there's now a folder, exams, and I think in everyone's, if you go to the exams folder, either yours or you should have access, I think, to the content library. Either one, I put the graded version, and if you want to see the ungraded, you can just click the PDF to download the ungraded. So you can see, or not graded, but the solution. So you can see the solutions to all the questions. You can also see that something went wrong on this page and everything, this page, this one. And all the answers got shifted to the left. I didn't notice that until this morning. So, yeah. So you can have all the solutions there. I did want to look at one problem in particular because this problem was the only one that people as a whole class did poorly on. A car starts from rest, and in 10 seconds, it has reached 60 miles per hour. What distance has the car covered in this time period in meters?
So,
Randy is ready.
I got right. Okay, so you want me to go with you?
Sure. What was the first thing you had to do? And other people besides Randy can jump in. I know he's excited, but what's the first thing you had to do?
Convert 60 miles per hour to miles per second.
Convert units. One student sadly missed both this one and the preceding problem simply because they didn't change units. Units are extremely important. As many people could tell you, like, for instance, NASA, who lost a Mars lander because they had two different scientists using different units. It's a millions of dollars error because of units. Yeah, you would hope at least. Okay, so 60 miles per hour, and you have miles on top, so I need a conversion factor with miles on bottom. And in your equation sheet, you have the conversion factor, 1,609.34 meters per mile. So now that would give me meters per hour, but I don't want per hour either. So remember, per hour means the hours are on bottom. So my conversion factor for time needs to have 1 hour on top, and I want to convert to seconds. There's 3,600 seconds in an hour, and that gives me 226.8. Is that right? 26.8 meters per second. I'm running on the memories from last night's calculations, so. Okay, so we have the final velocity. Now that we have the final velocity, now what do we do?
Come on, man. Plug that into it.
No, we haven't defined the acceleration view.
The average velocity is the initial plus the final divided by 2 if we have constant acceleration. Now, I realize the problem didn't say constant acceleration, but I emphasized you can only do constant acceleration problems unless you're in the calculus class. So all of our problems would be constant acceleration. So that's the average velocity, which of course is half of 26.8. I think we can all do 26.8 divided by 2 in our head, right? Don't mess with me. And so finally, we have distance is equal to V average delta T is equal to, hey, nice, 13.4 meters per second multiplied by 10 seconds equals 134 meters per second.
No, just meters.
Oops, yes, just meters. Thank you, sir.
I did it totally different.
There's lots of different ways you can do it. There's nothing wrong with doing it totally different if you did it correctly.
I did
Okay.
use acceleration problem, and then I plugged it in. I was like, I'm going to 0, and then 9.
Now, the reason I did not do it the way Sarah did it is because I didn't want to have to rely on the preceding problem for this. Because if that's the case, then if you did the preceding one wrong, this one's wrong. Okay, any questions about the exam? Or additional questions, I should say. Okay, no questions, then I am moving on. So, we spoke on Friday about forces, and we're going to do our first force problem type things today. In fact, I went into the class next door that Randy's in at the end of class, and I saw them doing problem that we're going to do in class today as well. So Randy's like getting extra exposure. So on last Friday, I listed these forces and talked briefly about them. I'm going to talk a little more carefully about some of them today. Do you remember what the equation for weight or the force of gravity is?
Mass times gravity.
Force of gravity is equal to mass times the acceleration of gravity. G is the same G we've been using. And I actually had some slides that I had at Friday's lecture I didn't get to go through Newton's universal law of gravitation. I'm not going to cover that today, so we'll just stick with force of gravity is mg. That's true as long as you're on the surface of the Earth. If you move farther away, it's going to change. If you move to a different planet, it's clearly going to be different. Normal force. What was the normal force? Well, what was the purpose? Well, I mean, description of the normal force. It's the thing that keeps you from going into a surface. So I'm standing on the ground. The ground is putting force on me to keep me from falling through it. And it's called normal force because its direction is the direction we call normal, which is the direction coming out of the surface. So it's not vertical, horizontal, that kind of thing. It's out of the surface, no matter what angle the surface is. It's the one that's coming out of it, not at an angle. Tension, I have slides on it, but not the next one. Tension is a force that's distributed through a string, and then springs. And springs is the first one I have something about. And I'm actually going to do, hey Judith, a demonstration here with tension. So I need a volunteer to come help a brother out.
But you're not done.
I'll have you know that I am proud of my heritage. My brother and sister being born in Liberia. I was raised in Africa, but I was born in the U.S. So what I need you to do is to take this meter stick and measure the position of the bottom of the spring. And you just tell me what the number is. So measure it just with that. And tell me what the number is. Okay, so she says 31.5.
Wait, do you need it up from the table?
Just like it is, yeah. So 31.5. Okay, now hang 100 grams from it and measure again to the bottom of the spring, not to the bottom of the mass. So now she's got some mass on there. Whoops.
41 and a half.
I'm a genius. I put 31.5 in the wrong spot. So this is 141 and a half?
Yes.
Okay, now replace the 100 with the 200.
$51 and a half.
Okay, and then add the 100 just from the bottom of that. Doing her experiment here for us all.
62 and a half.
And take both those off, or take that one off and put the other two. Yeah. You see the plan. There's a pattern here. So we're up to 400 grams hanging.
$73.
73.
One more?
Yep. Well, yeah, that works. I say take them off and put the 500 on, but that works as well.
83 and a half.
Okay. Oops, I put that the wrong place. Thank you. That was a very quick experiment to measure how much the spring stretches as we put forces on. And so we put forces incrementing by masses of 100 grams. How do I get a force based on a mass? The force of gravity was mass times gravity. Now, what was the acceleration of the masses once you put her hand there to stop it from moving? If the velocity was 0 and constant, what's the acceleration? 0. So the acceleration was 0, so Newton's second law says the net force acting on the mass was 0. When we had the force of gravity downward, something had to be pulling up. So that had to be the spring pulling up with a force that was equal to the force of gravity. So that force of gravity is also the spring force because those are the only things that we're acting on. So what we have here is a measurement of the spring force as a function of how much, the position of the spring bottom, which tells us how much it was stretching. Right, the first one, the one with the mass of 0, that was its unstretched length. Now, honestly, when this spring was made, it was made so that it would hold itself closed. Its unstretched length would actually be shorter than the spring is, so it would hold itself closed with certain force holding it closed. But it's been pulled too much. You might remember we talked about elasticity and plasticity in response to somebody's question. This has been stretched too much, so it had plastic deformation, a permanent deformation, and now its unstretched length is different. So when you look at this graph, let me cruise over. What do you notice about that graph? It's a straight line. And so up here in the corner, I just wrote on it in a way that didn't help us at all. We have the straight line equation. Y, what did we plot on the y-axis here? Force. Okay, so that was the spring force. So I have the force of the spring equals 0.0938. And then on the horizontal axis, it was position. So I'll just put x minus 2.9213. So there's the fit to the straight line. There's importance to this, that minus 2.9213, that would be how much I would have to compress this to make the bottom of the spring be at the top of my meter stick, right? Because that's just based on how we had our meter stick arranged. If I had the meter stick sitting up on a block, that number would have changed. So clearly that's not really an important number. It just has to do with how we set up the experiment. But then that 0.0938, That's measuring how much force changes as you stretch the spring. We call that the spring constant, and it depends on the construction of the spring. So that spring has that spring constant. If I take another spring, like for instance this one, made out of the same material actually, but clearly a different style, and it's going to have a clearly different spring constant. So the spring constant is unique to the spring based on how it's constructed, what it's constructed of, etc. So this here, we call the spring constant K, and we have the general equation, the force of the spring equals K. We put delta X to make sure we're talking about just how much the spring is stretched from its equilibrium position. Now there's one more technicality, but I better get to Russell before I forget. Which question, Russell?
So this spring constant unique to every single spring in the system?
Yeah. Now, one thing that I did not write that you will often see is a minus sign here. If you put vectors, then you have to have that minus sign. Because the spring force is what we call a restoring force. It will try to return the spring to its equilibrium length. So if you stretch it, it tries to pull it back. You compress it, it tries to push it out. So that's what the minus sign is indicating. And later on, when we get to oscillatory motion, that will be a very important concept indeed for us. So here you see it as the vector equation with the minus sign. Exactly what I wrote, isn't it? Why do I go through this? Because we're going to use springs and we need to be able to calculate the forces from them. And hopefully you can see very clearly from our demonstration why we have this linear relationship between the stretch length and the force the spring is producing. Then friction. We talked about how important friction is on Friday, but we didn't talk about exactly what causes it, I don't think. So this picture is a nice depiction of what actually causes friction. Now there's two things to be concerned about. One is, well, I think I have three things here, don't I? No, I have two. One is the forces between molecules. I mean, you never think, oh, my hand, there's atoms, molecules in my hand, and there's a force between the atoms in my hand and the atoms of the table. But there actually is. The closer I get, the stronger that force is. And so that's part of the frictional force. You know, you might imagine if you do things wrong, like you take two pieces of lead and you press them against each other, you could have bonds form, so it basically becomes one piece of lead, right?
Can't you do that in space?
Hmm?
Can you do that?
Well, yes. Yes, I believe you can. I've never been there, so I couldn't say for certain. So you have adhesion between atoms and molecules in one material and the next, and then you have rough surfaces. And I may or may not have done this in class on Friday. I frankly can't remember. But I always just like to use my fingers. My fingers are, one hand top of the other. My fingers will conform to the others, so it's kind of hard to slide them past. I have to raise my hand to get it past. But once I have it raised, if I keep going, it'll stay up there and it'll go more easily. You have the same thing with friction. If I have an object like this mass sitting on the table, right now there's going to be a little conformation between the surface of the table and the bottom of this. If I slide it, it will come out of that and it won't have quite as much friction while it's sliding than it had when it was stationary. It's much easier to recognize if you talk about like a rubber tire on asphalt. Because you know that rubber tire is deforming and conforming to the shape of the asphalt. And so then you're going to have much more friction than you would if it was sliding over the tops of the asphalt. So I like to talk about that so you understand what's causing the friction. It's not just, well, it's there, I know it's there, I see it every day. But think about what causes it. So because there's a difference between sliding, this is never going to work for me, between sliding and not sliding, we have two equations for friction. One for static friction, the one that's on the left, and one for kinetic friction, the one that's on the right. So what is that funny shaped character before Fn? Mu. It's the one I forgot to put, well, I didn't. I changed the font twice, but it changed back on me a third time and I didn't notice it. on the test, so I had to write the pressure. That's mu, the Greek letter M. That's what we use for our coefficient of friction. But we have two equations for the static case. And there is an error on this slide. I noticed it last year and forgot to change it and just used the same slide. Kinetic friction is equal. Static friction is less than or equal. It's kind of important. Static friction, the force of friction when something is not moving, is going to be whatever the force is necessary to keep it from sliding up to the maximum amount that it can produce. So right now, there's nothing trying to move this mass sideways, so the force of static friction is 0. If I push a little bit, it doesn't move because the force of static friction went up to be equal and opposite to the force I'm putting on it. If I push harder, it starts to slide, then we get to the kinetic friction realm. So if my force exceeds this force of static friction, then it starts sliding, and then we go to this where we have a constant force of friction. This mu sub k for kinetic friction, kinetic meaning motion, static meaning stationary. The coefficient for kinetic friction is always less than or equal to static friction. So a very practical example. You're driving your car and a dog jumps out in front of your car. What do? You slam on the brakes. What then? What?
You don't swerve.
Never swerve.
That's true. True story. I ran over a dog once.
Oh.
Back tires of my car ran over the dog. I'm driving down the road. About the time my front of my car is eating with the dog, he decides to run across the road and ran into my back tires. I went and talked to the homeowner, and she didn't really care. The dog was fine. And yeah, it was weird. She was a pre-vet student. Later on, because one of my physics grad students was rooming there with her as well, and they had an empty room, I lived in that house with her, and she was smart but odd. She went and tied the dog to somebody's front porch because nobody would come take it. Anyway, she's a vet. Anyhow, back to the important things. So you hit the brakes, you don't swerve because you don't want to crash, but you also don't want to hit the dog, so you hit the brakes. And most of us are going to panic and just push the brakes as hard as we can under the theory that the harder my foot is pushing on the brake, the faster I stop. Isn't that the theory that, okay, intellectually you may know better, but in the heat of the battle, you're just like, stop! And so your tires should naturally slide. But if your tires are naturally sliding, you don't have as big a frictional force as you would have if you were braking maximally without sliding. That's why we have anti-lock brakes. Anti-lock brakes, you push really hard on the brake, and the car says, oh, it feels like the tire is sliding. And so it lets off a little bit on the brake until it stops sliding, and then it immediately brakes harder again. And so your braking is pulsating because every time the tire starts to slide, it backs off, and then it starts raising the brake again. As a net result, the force of braking you get when your anti-lock brakes, okay, so you hit the brake pedal. Oh, I gotta use my finger. I'm really thinking. I told you I stayed up late last night grading, right? So I have force on this axis. And so when you hit the brakes, it comes up like this, and then it starts to slide, and then the anti-lock brakes kick in, and it goes like this. Whereas if the anti-lock brakes had not kicked in, once it started to slide, it would have gone like this. And so the average force you're getting from the anti-lock brakes is higher than you would get if you were skidding. Thus, you stop quicker. Better chance of not hitting the dog. Also, you could swerve if you were, going slow enough that you're not going to risk rolling the car or hitting anything like a tree or a person that's on the side of the road. So a little understanding about friction, how it works. The direction of the friction. Forces are vectors. Right now, what would you tell me about the force of friction acting on that mass?
It's less than or equal to something.
The static stuff.
Okay. That is true. It's less than or equal to, but it ends up being zero because there's nothing trying to push it. Right? Now, if I push it a little bit, then it's going to be less than or equal to mu static times force normal. What is force normal? The force the surface pushing on to keep from going into the surface. And then once I get it sliding, then it's the mu k times force normal. If I push on it and it doesn't slide, what direction is the force of friction?
Down.
Right.
It's opposing my force, so the net force is zero. It's going to be whatever direction is necessary to keep it from sliding. Now, if it's sliding, I can make it slide and I'm not touching anymore. What direction is the force of, what kind of friction is it if it's sliding? Kinetic. What direction is that?
Still back.
It's going to be opposite the direction that it's sliding on the surface. So it's slowing it down. Now, sometimes we can get confused on this, like you put a box on the tailgate of your car. And when you start from a stoplight, let's assume that it doesn't slide. What direction is the force of friction on the box if it's not sliding?
Oh, it goes backward. Or the car's moving forward, but then it's kind of in one place.
It would stay in one place, so the car is having to pull it forward, so that force of static friction is going forward with the car to keep it from sliding.
Yes.
Right, and so it's still static friction. It's moving, but it's not moving against the surface, so it's static. All right, let's move on to the next. Coefficients of friction vary depending on the surfaces. So when I was talking about this in class on Friday, I talked about like being on a wet ice surface. Let's see, do I have wet ice on there? Shoes on ice. Notice how low that is. And if you have water, it just makes it lower. Something that's very cool to note, bone lubricated by synovial fluid has a super, super low coefficient of friction. The friction between your bones is really, really small. Unless you put really big forces there. Well, then you can make it big, even though the coefficient's small. You can get a pretty big frictional force if you like have a lot of weight you're carrying around. What's the biggest friction coefficient in this table?
Rubber on concrete. That's true.
That. For a lot of people used to think, for some random reason, that 1 would be the highest that you could ever get. But if you think about it, no, that shouldn't be the case, because I could glue that thing on there, and that glue would kind of be, glue on wood, and it'd have a bigger than 1. For dragsters these days, they get coefficients of friction between the tire and the road that's much bigger than 1. Get more friction. What makes a car go? It's the force of friction. You get more friction, you can get more force making the car go forward. If you don't have friction, it doesn't matter what kind of engine you have, you're not going to get very much forward acceleration. There's also really cool physics in dragsters. I showed you a picture but didn't have time to talk about it 2 weeks ago or so. But when dragsters come out, their tires look like they're really flat, right? And then when they start up and you look at a freeze frame, you see that the tires are all kinds of warped and stuff. That's intentional. First of all, the tires look flat because they have a smaller radius. They are flat. And that means that you'll have more force delivered for the same amount of torque. And so they can get a better start. But then the deformation is because their tires are doing effectively the same thing as anti-lock brakes. The tire grabs and you have static friction until it deforms enough that it slips and it slaps back and then it grabs again. And so they're basically getting static friction when they're peeling out because of the design of the tires. It's kind of like anti-lock brakes in reverse. It's pretty amazing. There's a lot of physics that goes into any of your sporting things. I mean, anything in life in general, but sports is where you see it a lot. Air resistance. I have two equations here for air resistance. The one on the left is called the drag force, and the drag force is the force you get when you have a turbulent flow. And that drag force is dependent on speed squared.
So turbulent flow, what does that mean?
That means that you have, in this case, you're in air. Any fluid, it would be true. But you have the fluid is doing stuff like this instead of smoothly flowing. So that force is proportional to speed squared. So if you double your speed, what happens to the force? Should quadruple. Now, when you're falling, like the skydiver here, you have forces acting on you. You have the force of gravity pulling you down. And then you have, in this case, it's actually going to be something like at an angle, but I'm just going to pretend it's a vertical. The force of drag pushing you up. According to Newton's second law, if one of those is bigger than the other, then you're going to have an acceleration. And so when you first fall off of let's say you're base jumping from the top of a bridge. When you first fall off that bridge, you'd have a very low drag force. In fact, initially you'd be with that Stokes force that's proportional to speed. So you have a very low force of drag. Force of gravity is going to be large, and you accelerate essentially at the acceleration due to gravity. But as you go faster, that drag force gets bigger, and your net force gets smaller. So your acceleration becomes less and less until you reach the speed where your drag force equals the force of gravity, and then your net force is zero. If the net force is zero, how's your velocity going to change? It doesn't, that's right. Max was shaking his head just because he did it with his head rather than audible. So that's what terminal velocity is all about. Terminal velocity is reached when the air resistance force, whether it's the Stokes law or the drag force, is equal to the force that's pushing the object. Russell.
Isn't like squirrels have like a crazy terminal velocity where they can't die from height?
That's what I've read, yes. Squirrels, unless you've got a squirrel that's got some problems, should not be damaged by falling out of a tree. Because they have this stuff here, that's the viscosity of air, that's the cross-sectional surface area. That's a constant, it has to do with the fluid. That stuff is big enough that their terminal velocity is low enough that they can withstand the impact. So basically anything smaller than a squirrel should be safe to fall from any height.
If it was a really fat squirrel.
If it was a really fat squirrel, now it's a legit question even though it's a funny question. If it's a fat squirrel, what does that change for the forces on it? The downward force due to gravity is bigger. But the cross-sectional area does grow some, but not as much. And so it would have a higher terminal velocity and more likely to be injured. But it also has better pattern. Russell.
Because Max are about as big as squirrels, and they can definitely die by throwing them off something.
I've never tried that. I did experiments with my cat. We'll talk about that later. I was like 7 years old. I had the brain of a scientist that was 7 years old. Okay. I need to do some problems, and I've got to get through these forces before we do them. Tension, we've already talked about tension, so I'm going to just move through there. Here's our first problem and how to solve a problem. So we have Tarzan. Oh, brother. He's hanging from a rope or a vine. And a problem says Tarzan has a mass of 84 kilograms and asks us what the tension in the vine is. Now, what did I tell you about the force that tension applies when it touches something? This would go back to Friday. The tension force is always equal to the tension in the direction away from the object it's touching. So since Tarzan is holding to the rope here, the force of tension, and I always use F sub T, not just T, the force of tension is directed upward with whatever the tension is in the rope. What else is going to act on Tarzan besides the rope? Gravity. So he has a force of gravity. Our textbook uses W, but I always put force of gravity acting downward. And if Tarzan is just hanging here doing nothing, what is his acceleration? 0. And so we look at this and we say, first thing I'm going to do is draw the forces. Now, as far as I'm concerned, this diagram right here is sufficient. There is a technical definition of I'll call it a free body diagram, or FBD for short. The technical definition of a free body diagram is you take your object of interest in this column. I have to decide what's my object of interest. So what do you think it is? Tarzan. Tarzan is my object. And Tarzan becomes a dot. So right here next to my line, you see a dot. That's Tarzan. And then on that dot, I show all of the forces that are acting on my object. Not forces that the object is applying to other things, but the forces that are acting on my object. So I have the force of tension acting on Tarzan in the upward direction, and the force of gravity acting on Tarzan in the downward direction. So this here we call a free body diagram. Those are really important. They have but one purpose: to allow us to apply Newton's second law in an accurate fashion. So we make these free body diagrams so we can apply Newton's second law. Now for today, all of our situations are going to have the acceleration is 0. But what is Newton's second law? Okay, I think I heard you say sum of, which is super important. Sum of the forces acting on an object, so in this case that'd be acting on Tarzan, is equal to the mass of that self-same object, so the mass of Tarzan, multiplied by the acceleration of that object. Now it's a vector equation, so I'll put my vector signs. But just like with motion, we break things into directions and it applies in each direction independently. So it applies in the vertical direction, also in the horizontal direction. Or if I tilt my directions, just make sure they're 90 degrees from each other. So in this case, the acceleration is 0. And so applying that, I'm going to have the sum of the forces. If I consider up positive, then I have the force of tension is acting up minus the force of gravity acting down equals 0 because the acceleration is 0. Now, it doesn't take a genius to take this and solve it for tension. What's tension equal to?
Negative force of gravity.
Yeah, and that's what I just did by implication when we did the experiment here with Andy. I just said it's going to have to be the same as the force of gravity, acting in the opposite direction. Yes, Max?
This might seem stupid, but so like if you're not moving, you're not accelerating.
Correct.
To each other, right?
Mm-hmm.
And if gravity is more, obviously the rope will break and you fall. Like what happens if tension is a greater force than gravity?
If tension is a greater force than gravity, you're going to accelerate upward.
Like a spring?
Yeah, like if you're on a bungee cord and you've stretched it enough that the tension force is bigger than the force of gravity, you're going to accelerate upwards. So you're going to slow down and then go back up.
So does the tension force become like a spin force in that instance?
Well, it depends on your material. With the bungee cord, it's not going to be able to give you the repulsive force, only the attractive force. By the way, I did mention in class last Friday, our ideal string does not stretch and has no mass, because of course that exists. Okay, finally, just to remind ourselves, what is the equation for force of gravity? Is mg. So in this case, that's 84.0 kilograms times 9.80 meters per second squared, which gives us somewhere in the ballpark of 800 newtons. And so that's what the tension in that rope would be. Notice I'm using newtons. A kilogram times a meter per second squared is a newton. I had to put this in. Tendons are things in our body that connect muscles to bones. And I have this little mark of Zorro on my finger from where I was playing flag football. My finger got caught in the guy's flag belt and yoink, it busted that tendon. So it broke right there. And then like 3 or 4 years ago, the exact same thing happened to my son. And then like a year after that, my wife had this one here break. So everyone in my household has had a finger tendon break. All of us from playing football, though in her case, it was trying to catch a football and jamming the finger. All right, a problem. A problem just like Randy had to do an hour ago. Okay, Randy's like, I got this. So here we have a person with a weight of 840 newtons. It doesn't give us his mass, it gives us his weight. What's the difference in mass and weight?
Weight accounts for acceleration.
Okay, weight is the force due to gravity. Mass is the amount of stuff present. And so the weight is proportional to the acceleration of gravity and the mass. So it gives us that. And then he's on a tightrope with the ropes making a 5-degree angle on both sides. And it asks us, what's the tension in the rope? Now, when you look at this, I hope, just because I don't want you guys to be so much smarter than me, that you're like, I don't see that there's a way through this. I got some facts, but I don't have any answers. But there is a way through this. And so we're going to work it out. I'm going to model problem solving for you. So we'll go to OneNote so I can... Well, I put the wrong picture in. Well, this is fundamentally the same problem. It's just a different, this is the one I was going to have you do, and I put the wrong picture in for the first one. So I'm going to do this problem instead. It's fundamentally the same problem. It's just the version I was going to have you guys do if I finish mine in time. So here, instead of having a force that is, actually, no, it's exactly the same. We still know the force, except for now it's 95 newtons.
Is it newtons? It's in pounds.
Oh, pounds. Oh, my goodness. Okay, it's in pounds, something that we never use. Why do we use LBS for pounds? Libras, yeah. That's the abbreviation for Libras, 95 Libras. Okay, so we've got that force, and we want to find what the tension is, and we have a 5-degree angle. When I do a force problem, as with all problems, the first thing you need to do is draw a diagram. Well, this has a diagram for us. I'm going to then go a step further and identify identify the object I'm looking at and all the forces acting on that object. So the thing you have to ask now, it's kind of a tricky question, is what is my object? What do you suppose the object should be? You can come up with a lot of answers. There's only one right one. But that doesn't mean that it's bad to come up with the wrong answer. What do you think the object should be? Okay? Judith says the chain. Max says the tree.
I say the U because it's asking me what tension U can I apply.
Okay? So Andy says the U.
Like me.
Yes. I'm with you. It actually doesn't really matter too much if you use U versus the chain, but what I'm going to use is the link of the chain that I'm pushing on. The link of the chain I'm pushing on, because if it's me, you know what I have to worry about? I have to worry about, okay, the tension is applied to me from this chain, and then I have the force of friction on my feet, and it becomes a little more complicated. If I keep it that link of chain, it'll be less complicated. Now notice that this is all horizontal. all the forces are horizontal. So I'm simply going to work in the horizontal plane. I'm going to define X and Y like this, and Z would be up and down, and I don't care about it. I'm only going to work in the horizontal plane. I now need to draw my free body diagram for my object. I don't know the mass of that linkage chain, right? But I know the acceleration of that linkage chain is approximately 0, and so I don't care about the mass. That's kind of an important thing to think through as well. So on that link of chain, what forces are acting on the link of chain? Okay, somebody said gravity, but that's in the vertical direction, and I'm ignoring the vertical direction. So ignoring the vertical, only looking horizontal, what forces are acting on that link of chain? Okay, I have a force of tension. I have the force of tension on both sides of that link. And the force of tension is always going away from the object. So I'm going to have force tension 1 and force tension 2. Those arrows really should be the same length, because I am dealing in the perfect physics universe. So I have those two forces, and then what else do I have? The what? Okay, that is something I'm going to have to add to this, but I'm asking specifically what forces are acting on my object, and then I'll get to the angle, because that's a very important thing. Okay, that force, they called it force perpendicular. Now I'm going to go with what Claudia said. I need to add to this my angles, because they're kind of important. So my angles, there's a horizontal line. I can actually make a truly horizontal line. It's one of my skills. I can also make a perfectly straight line. It's another one of my skills. Line is yet another one of my skills. Now, I just put 5 degrees. I don't know if it gave me more significant digits or not, but for today, we're focusing on the mechanism and not significant digits. I've got this drawn. Now, what do I do? What was the purpose of the free body diagram? Oh, man, time's out. Well, it's important to identify the forces so we can apply it to Newton's second law. So now I apply Newton's second law. Sum of the forces equals mass times acceleration. There's 2 ways of doing it. In this case, what's the acceleration? If I have only 3 vectors, making a triangle is probably your fastest way. If I have more than 3 vectors, then you're going to be stuck. Break each vector into components and apply this in the x direction, and then apply again in the y direction. In this case, because I only have 3, I'm good at drawing. So this is force tension 1, force perpendicular, force tension 2, and I knew that it was 5 degrees there and 5 degrees there, so that makes this whole angle 10 degrees. So what do I know? I know these 2 angles are equal, so those angles have to be 85 degrees each. So I know all of the angles, and I know one of the sides. The law of sines will kick out for me what the tension is instantly. So using the law of sines, I have sine theta 1 over, well, I'll just put in the sine of 10 degrees. That's this angle right here. Over force perpendicular is equal to the sine of 85 degrees, either one of these angles, over the force tension And so the tension is equal to sine 85 degrees over sine of 10 degrees times the force perpendicular. That's the quick way to do it because I only had 3 to contend with. We're out of time. What we saw today is a review of the forces again, making sure we know what each one is, and our first problems. Yay!
Yeah.